Now let's take a problem which is based on perfect case equation. So I am just writing the problem first, which is based on perfect case equation. So problem I am writing here. A 1 meter cube tank is filled with a gas at room temperature 20 degrees centigrade and pressure 100 kilopascal. How much mass how much mass there how much mass is there if the gas is A point, the gas is air, B point, the gas is neon, or C point, the gas is propane. So in this problem we have to find out the mass of the gas. If gas is air, neon, propane, here volume is given, temperature and pressure is also given. So first of all, just write the given things. Temperature we are having 20 degrees centigrade. So in terms of Kelvin, 273 is 20 plus 2, 293 Kelvin. Pressure we are having 100 kilopascal. Now molecular mass of the air we know 29. Molecular mass of neon is 20 and molecular mass of propane is 44. So now we have to use the perfect gas equation where we are using the characteristics gas constant. So we have to use PV equals to mRT, and we know the value of R we can easily find out with the help of relation between R and R. So just for air, so R for air, R will be RU by M. So we can write here that is 8314 divided by 29. So now if we calculate mass of the air here, we have to write PV divided by RT. So P we are having 100 kilopascal, that is 10 to the power 5, into volume we are having, that is 1 meter cube. We are having R, that is R 8314 by 29, 8314 by 29, and temperature we are having 293. So mass is coming 1.19 kg. Similarly, in B part we are having neon. So for neon, we will calculate R is RU by M of neon. So again 8314 divided by 20. So mass of the neon we can calculate by PV by RT similar way. So again 10 to the power 5 into 1 divided by 8314 by 20, it is RU R into 293. So we will get 0.82 kg. Similarly, for part C, that is for propane, we can find out characteristics gas constant by RU by M molecular mass for propane, that is 8314 divided by 44. So mass of the propane we can find out by PV by RT, same equation, 10 to the power 5, volume is 1 meter cube, R for propane 8314 by 44, and T is 293. If we calculate it, we will get 1.806 kg. So by this way we can find out mass of the different gases easily. Take another problem. It's very interesting thermodynamics problem. I'm just writing the problem here first and then we will. Stationary mass of gas. Uh, stationary mass of gas is compressed without friction from an from initial state of 0.3 meter cube and 0.105 megapascal to final state of final state of 0.15 meter cube and 0.105 megapascal. The pressure remaining constant during the process there is transfer of 37.6 kilojoule of heat from the gas during the process. How much does the internal energy of the gas change? So again I will repeat the problem. There is a stationary mass of gas that is compressed without friction from an initial state of 0.3 meter cube to the 0.15 meter cube by keeping the pressure constant, that is 0.105 megapascal. There is a transfer of 37.6 kilojoule of heat from the gas during the process. So how we have to find out the change in internal energy. So this problem is purely based on first law of thermodynamics. So now I have to write the first law of thermodynamics, and before that, before writing first law of thermodynamics, just to calculate the work done in this process. So first calculate work done. So work done in this case, here the pressure is constant, so we can write P V2 minus V1. So pressure here, that is constant, 0.105. Final volume, that is 0.15. Initial volume, that is 0.30. So here I am having 0.105 into minus 0.15. So I am having minus of 15.75 kg. So negative sign is showing work done on the system. Similarly, we are having the heat transfer, that is Q. There is a transfer of 37.6 kg of heat from the gas, means the heat lost by the system, so that is minus 37.6 kg. Now we have to apply the first law of thermodynamics. First law of thermodynamics. I am applying just the first law of thermodynamics. So that is nothing but Q equals to del U plus W. Here Q minus 37.6, del U, W is minus 15.75. And then if I talk about del U, it will be minus 37.6 plus 15.75. So del U, that is change in internal energy, be minus 21.45 kJ. So it means internal energy, internal energy of system will decrease by 21.85 kJ. That is the correct answer. Let's take another problem. First I am writing the problem here and then we will solve it. When a system is taken from state A to state B along the path ACB, 84 kilojoule of heat flow into the system, and system does 32 kilojoule of work. So A, how much will the heat that flows into the system along the path ADB, along the path ADB, if the work done is 10.5 kilojoule. B part, when the system is returned from B to A along the curved path, the work done on the system is 21 kg. Does the system absorb or liberate heat, and how much of heat is absorbed or liberated. Part C, if UA is 0, UA is internal energy at A is 0, and UD is 42 kilojoule. Find the heat absorbed in the process AD and D. So these are the three parts we have to solve. First of all, I will draw the diagram given in the problem. And Y there is a pressure, on X there is a volume. Here we are having a rectangular block, and here we are having a curve, and this one is A, B, this one is C and D, and these are the various parts shown by A. So now let's take a first part. A. So here it is mentioned when a system is taken from A to B along the path ACB. Now we have to consider ACB. 84 kg of heat flows into the system. So I can write QACB. Heat supplied to the system, that is positive 84 kg. And system does 32 kg of work. So work done through ACB is 30. Work done by the system is positive. So I am taking the positive side. So now if I apply the first law of thermodynamics for ACB path, so we are having QACB equals to UB, that is final, UA initial plus WACB. So 84 equals to UB minus UA plus 32. So 84 minus 32, I will get UB minus UA. UB minus UA. So 84 minus 32, 52 kilojoule, I will get UB minus UA. So I already got the value of UB minus UA, that is 52 kilojoule. Now in the problem A, it is given how much will the heat that flows into the system along the path ADB if the work done is 10.5. Now we have to consider path ADB. So on consider path ADB. So we have to go by ADB. So now applying the first law of thermodynamics for path ADB. So Q ADB equals to UB minus UA plus WADB. So they mention that is work done is 10.5 kg, means that is positive work done, and we have to find out the heat flows, that is AD. UB minus UA we have already calculated, that is 52, and work done that is mentioned, that is 10.5. So QADB will be 52 plus 10.5, that is 62.5 kJ. So this one is the desired answer for part A. Now let's come to the part B. So in part B, it is given when the system is returned from B to A. So process is from B to A. Process B to A. So final is A, initial is B. Along the curved path, the work done on the system is 21 kg. Work done on the system. So work done on the system means negative minus 21 kg. We have to find out the heat, that is PA. So now again apply first law of thermodynamics for this process BA. So QBA equals to final is QA initial B WBA. So now we know UB minus UA is 52. So UA minus UB will be minus 52 kilojoule. So now QBA, UA minus UB minus 52, and work done on the system, that is minus, because work done on the system, so minus 21. So QBA will be minus 73 kg. So negative sign shows system is liberating 73 kilojoule heat. Now let's come to the part C. In C, UA is 0 and UD is 42 kilojoule. Find the heat absorbed in the process AD and DB. AD and DB. So now apply the first law of thermodynamics for the process for the cycle ATB. Part C, we can write WADB is WAD plus WAB. So here if you see WAD or WDB, if you see here in this diagram, WDB will be 0 because it's a constant volume process. So we can write WADB equals to WAD, and we have already calculated WAD, that is 10.5 kilojoule. That is 10.5 kilojoule. Apply first law of thermodynamics for process AD. On applying first law of thermodynamics for AD process. So then I can write QAD equals to UD minus UA, because D is final, A is initial, plus WAD. So QAD in part C, UD is mentioned 42, UA is mentioned 0, and WAD is already calculated 10.5. So 10.5. So we are having QAD will be 52.5 kilojoule. In part A, we have already calculated the value of QADB, that is 62.5 kilojoule. So I can write QADB equals to QAD plus QDB. So QAD is 62.5 kilojoule, and QAD I have already calculated 52.5 plus QDB. So QDB will be 62.5 minus 52.5 equals to 10 kilojoule. So by applying the first law of thermodynamics and the properties of the point function, we can easily find out the values of unknowns in terms of work done, in terms of heat transfer.